Worksheet 12. Solve for all values of x between 0 and 2 pi. Well, so once I see this interval, I know that I'm dealing with radians. So let's go about solving this. First, I need to find the value for x. To do that, I'm going to isolate the function containing it, which is sine for the first one. So I end up with rad2 sine of x equals 1. The divisible side's by rad2. End up with sine of x equals 1 over square root of 2, which is just the square root of 2 over 2 when I rationalize the denominator. And the reference angle, which gives me square root of 2 over 2 for sine, would be pi over 4 in radians, or 45 degrees in degrees. So once I have my reference angle, I can see that sine is positive. So I'm going to consider the quadrants in which sine is positive. A smart trig class. All are positive in quadrant 1, and only sine is positive in quadrant 2. So I'm either in quadrant 1 or quadrant 2. Once I know that, I can find my reference angles in those quadrants. Pi over 4 in quadrant 1 is pi over 4. And this is pi, so if my reference angle here is pi over 4, 1 minus 1/4 is 3/4 of pi, or 3 pi over 4. So those are going to be my two values for x. Taking a look at the second one. Again, I'm going to try to solve this for x. I see that there's a common factor of cosine over here, and that this is already equal to 0. So if it's already equal to 0, I know that one of its factors must be 0. So if I factor out that GCF, left with this, or either cosine of x is 0, or cosine of x equals 1. It's the only way that expression will be 0. 0 is a midline crossing for the graph of cosine, and 1 is a maximum for the graph of cosine. So these are actually the special cases of the quadrant angles. If I look at my quadrant angles, it's 0, pi over 2, pi, 3 pi over 2. On my unit circle, I have 4 special points, which are the quadrant angles. This is the point 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Remember that each of these points are labeled cosine, sine. Cosine in the x direction, sine in the y direction. So if I want to see where cosine of x equals 0, I'm going to find where the x values are 0, which happen here and here. So the solutions would be pi over 2 and 3 pi over 2 from this equation. And where cosine of x equals 1 is right here. The value of x equals 1. Don't be fooled by this one. This is negative 1, which is not the same as 1. So the only value here will be 0. My final solution is bringing all 3 of these together. Is x is either 0, pi over 2, 3, or 3 pi over 2. Again, for c, I'm going to factor, but notice I don't yet have 0 on the right-hand side, so I'm going to bring this over before I factor. Cosine squared x minus 3 cosine x minus 4 equals 0, which factors to cosine x minus 4, cosine x plus 1. So either cosine of x equals 4 or cosine of x equals negative 1. Well, remember from our last example that cosine of x will equal negative 1 at pi degrees. So this will be my solution between 0 and 2 pi. And cosine of x equals 4, well, the upper bound, or the maximum for the graph of cosine is 1. It's the maximum of its range, so it will never equal 4. I will reject this equation. So the only solution I get is x equals pi. That's the only time this equation will be true. The next one, again, I see I have quadratic terms, so maybe I'm going to have to try to factor, but my first main problem is that I have one graph of sine, or one function of sine, and one function of cosine. So what I'm going to try to do is convert this into an equation of a single function. So to do that, I'm going to replace cosine squared of x with its identity, 1 minus sine squared of x. So I have 3 sine squared of x minus 1 minus sine squared of x equals 1. I distribute this negative. I will end up with 4 sine squared of x minus 1 equals 1, or 4 sine squared of x equals 2, so sine squared equals 1/2. Or if I take square roots, remember whenever I take square roots with a variable involved, x in this case, I also have to account for the positive and negative solution. So I end up with sine of x equals plus or minus 1 over rad 2, which is plus or minus rad 2 over 2. This is not one of my quadrant angles. It's not a maximum, a minimum, or something that would be through the 0. So I'm going to use reference angle. The reference angle in this case would be pi over 4. That's when sine of x equals rad 2 over 2. And then the sign, the positive and negative, tells me which quadrants I'm in. A smart trig class. Sine is positive in quadrant 1 and quadrant 2, and it's negative in quadrant 3 and quadrant 4. So I'm actually in all 4 quadrants in this example. So I have a quadrant 1, 2, 3, and 4 solution. Here's my reference angle in each of these quadrants. So in quadrant 1, just pi over 4. In quadrant 2, I'm pi minus pi over 4, which is 3 pi over 4. In quadrant 3, I'm pi plus 3 pi over plus pi over 4, which is 5 pi over 4. And in quadrant 4, I'm 2 pi minus pi over 4, which would be 7 pi over 4. So x has to be one of these 4 solutions. The last one, I will admit, is an unfortunate example on my part. For this one, I did not give you radians or degrees. I did not give you an interval, so you have to solve for all values of x. You can do it in either radians or degrees. I'm going to do it in radians. The reason I say it's an unfortunate example is it doesn't come out to a nice reference angle, so I'm going to have to approximate, so I'm going to round to the 1,000th, and I'm going to do mine in radians. Okay. For this one, first, I'm going to notice that again I have a function of an equation of 2 different functions. So here I have sine, here I have cosine. I'm going to have to convert one to the other. I notice that I only have a single factor of sine here, but I have 2 factors of cosine, and I have an identity for cosine squared. So I'm going to replace the cosine first. So it'll be negative 5 times 1 minus sine squared x plus 9 sine x equals negative 3. When I bring this all together in combine like terms, I get 5 sine squared x plus 9 sine x minus 5 equals negative 3. So 5 sine squared x plus 9 sine x minus 2 equals 0. From here, in a factor, you can do this using AC method. I'm going to look at the sum and the product. I have a sum of positive 9, a product of negative 10, the A term times the C term, hence AC method. Numbers that multiply and add to that would be negative 10 and positive 1. So I'm going to split my middle term, 9 sine x, into plus 10 sine x minus sine x. And then bring down my other terms, negative 2 equals 0, and 5 sine squared x. I'm then going to look at my first 2 terms, factor out their GCF, which is 5 sine x sine x plus 2. And then on my second two terms, I have a GCF of -1, so this will be negative sine x plus 2 equals 0. And now I have a common factor of sine x plus 2, so I'll factor that out. I get sine x plus 2 times 5 sine x minus 1 equals 0, which tells me that either sine of x equals -2 or sine of x equals 1/5. Well, since the range of sine of x is from -1 to 1, this is out of its range, which just means it's rejected. So the only solution I have is this one. And when I solve that for x, I'm going to need more room. When I solve that for x, I get that x equals sine inverse of 1/5, which is, if I want that value, I can go to my calculator. When I go to type this in my calculator, since I was doing this in radians, I'm going to check my mode. I am in radian mode. If I was a degree, I would change it to this. I'm going to type in sine inverse of 1/5. I get 0.201, which rounded to the nearest thousandth is 0.201. That's its approximate value. And then here's the tricky part. The question said all values of x. Now, for all values of x, in this case, since this is positive, I'm in either quadrant 1 or quadrant 2. Here's my reference angle of 0.201. Here's my reference angle over here of 0.201. Well, in quadrant 1, I have a solution of 0.201 as a reference, and in quadrant 2, I have a solution of pi minus 0.201. So if I want that to the nearest thousandth, I'm going to go back to my calculator, type in second pi, and subtract that answer, second answer. 2.940. So 2.940 would be my solution of quadrant 2. Now, all values of x, not within a specific interval, so not only is this a solution of quadrant 1, but if I rotate it around 2 pi, or 1 full revolution, that would be another one. I could also go around another full revolution. In fact, any multiples of revolutions I could go around and get a similar solution. Same thing would be true if I subtracted off a full revolution. So not only is 0.201 a solution, but plus or minus 2 pi, which is a full revolution, times any number, any integer value, would give me another solution. And for the quadrant 2 one, 2.940 plus or minus any number of full revolutions as well. This is the solution set of all possible solutions for this equation.